In this example, we will be working on the topic of static equilibrium. So first, let's review the condition of static equilibrium. So first, we need to make sure that the total force is 0 so that the system is under translational equilibrium. Also, we need to make sure the total torque is 0 so that the system is under rotational equilibrium. So based on this, let's look at this example. We have a ladder of length of 10 meters resting against a vertical wall. The mass of the ladder is 4 kilograms, and it makes an angle of 53 degrees with the floor. There is no friction between the ladder and the wall. But apparently, there must be a static friction between the ladder and the floor. Let's label it as Fs. Because if there's no Fs, obviously the ladder would like to slide like this. So first of all, let's first set up the free body diagram of this ladder. Here we already have Fs, and we also have a normal force here. We labeled that M1. And we have weight, that is mg. And we have another normal force from the wall. Let's label that N2. So now we can set up the first translational equilibrium equation. We can do this along horizontal and vertical direction separately. So in the x direction, we have N2 equals Fs. And along vertical direction, we have N1 equals mg. Here I want to emphasize that even though the friction of the coefficient of static friction here, mu s equals 0.5 is given, it can only give us the upper limit of static friction. So Fs, we know its upper limit is Fs times N1. So at this point, Fs is still unknown. So to solve this problem, we need extra information. That is, we can obtain from the second equilibrium condition. So to work on the torque, first of all, we need a pivot. So here, let's first set up the pivot here. I'll show you later that the choice of pivot is actually not unique. You can definitely pick up other pivots. I'll show you later. But now, let's first look at the pivot here. If we put the pivot here, then we know N1 and Fs apply no torque on the ladder. So here, mg will provide a torque so that the ladder would like to rotate clockwise, while N2 will provide a torque so that the ladder would like to rotate counterclockwise. So the total torque here equals the torque from mg, that is mg times half of L times cosine 53 degree and minus the torque from N2 times L times sine 53 and equals to 0. So up to here, we already have 3 equations. Let's put them as 1, 2, and 3. And here we find that N2 is unknown, N1 is unknown, and Fs is unknown. So we have 3 unknowns with 3 equations. We can definitely solve them. So let's first look at question A. What is the normal force exert on the ladder? This is easy. Based on equation 2, we know N1 equals mg. It equals 4 kilogram times 9.8 meter per second square. It equals 39.2 Newton. This is easy. And for the friction force, Fs, we know it equals N2. So why don't we first find out what N2 is? We can do this based on equation 3. So here in equation 3, we can simply cancel L so that we have mg times half cosine 53 degree equals N2 times sine 53 degree. We have N2 equals mg divided by 2 tangent 53 degree. If we plug in the number, 4 kilogram times 9.8 meter per second square times 2 times tangent 53, we end up having 14.7 Newton. That's the N2. So now we go back to equation 1. Now we know Fs equals to N2. It equals 14.7 Newton. Let's check if the result makes sense. Here we have mu s times N1 that sets the upper limit of Fs. It equals 0.5 times N1, and we know N1 is 39.2 Newton. And we will have the Fs equals 19.6 Newton. Which makes sense because we end up having Fs equals 14.7 Newton. It is exactly smaller than this upper limit. So we know here this result is correct.